Hello, it's Mr. Hodgkinson here. Going to be talking about fibre optic cables and kind of how they carry digital signals, what the benefits are, what the problems can be, and how we get around the problems. So I think most of you are aware of kind of what fibre optics look like. So it's going to be a thread of very, very, very thin glass, and it uses the principle of total internal reflection to make light, I would say bounce, but obviously I wouldn't use the word bounce because that's wrong, to make light reflect along inside the fibre optic cable. So light will enter it, it will be slightly refracted, and it will hit the outside. If you remember the critical angle, so the critical angle is the point at which light stops being refracted and starts being reflected back into the medium, whatever it's travelling in. So at this point, if that angle is greater than the critical angle, then the light will be reflected back in, and that will happen, and eventually the light will come out the other end. I'm just going to draw arrows in. That's a good habit to get into. Most diagrams want arrows. So how we use this to communicate is we will send pulses of light through this end, and then the other end will receive those pulses of light. It will be a digital signal. So we might have a pulse, and the peak will correspond to 1, the trough will correspond to 0, and we end up with a digital signal. Now the advantages of this, lots of people are very quick to say it's faster than using an electrical signal. And that's true, but it's not really an advantage. There's a lot less noise, there's a lot less disturbance, and you can have more information being sent simultaneously. It's a little bit more complicated than just light being reflected down a glass fibre. There's something called the cladding, which surrounds it. And actually, really, there's probably 2 layers of cladding. So there's outer cladding, which exists just to protect it. So it's a thick material, because it's going to be quite delicate. It's a shard of glass. So there's the outer cladding, which is existing as a protective, and then there's the inner cladding, and that has a function to do with the refraction. And the function of the inner cladding is it's a lower refractive index than the fibre optic itself. That lowers the critical angle, and it makes it more likely for refraction to happen. Some of the problems with this, something called material absorption. So the glass is as pure as it can be, but it's not going to be entirely pure. There's going to be impurities, and that's going to mean that some of the light is absorbed, and so over time that peak that's received is going to have a smaller amplitude, and over a big enough distance that peak will drop to 0, and then the ones will be indistinguishable from the zeros, and we won't have a digital signal. So there's material absorption, which is a problem. There's something called modal dispersion. So you'll remember that refraction is determined by wavelength as well as material. So different wavelengths refract at different amounts. So if we have red light or blue light entering this, they're going to be refracted by different amounts. And that's going to, I'll come on to something called pulse broadening, I'll come on to that in a minute. The way we get around material absorption is if we're going to stretch a fibre optic cable from London to New York, and there is one under the Atlantic Ocean, it isn't one continuing cable. It's got what's called relay stations. So after every, to be honest, I don't know the distance, but after every, let's say 10 miles, 50 miles, something in that region, there's a relay station which just boosts the signal. So the energy that's been lost to being absorbed is kind of boosted back up, it's increased, so that signal is able to reach New York. Modal dispersion is a bit more complicated to fix. So modal dispersion can happen when light of different wavelengths enters the fibre, and it can happen if the light entering it is entering at a slightly different angle. Hang on, this is not as high tech as I'd have hoped for. So, if we have light enter, and whether by being a different wavelength or at a different angle, if it enters at different paths, then we've got a problem. Because if those two beams of light are taking different paths, they're going to arrive at different times. So, where we start off with really defined peaks and troughs, if this peak is taking a shorter path than this pulse of information, it's going to catch it up. So eventually, those really distinct peaks and troughs are going to stop being distinct, and they're going to become kind of spread out. It's called pulse broadening when the peaks are broadened, and eventually, actually, they're going to catch each other up until they're indistinguishable from one another. So the problem with modal dispersion, that's the different wavelengths taking a different path, it will take a different time, and so those distinct peaks will be spread out. There's two ways around this. The first way is to only use monochromatic light. Now, we've come across this word before. You know what mono means if you think about monorail or monobrow. It means one, it means singular. I said monochromatic. Chromatic we know relates to colour. So monochromatic means the same wavelength. So you use monochromatic light, so you've not got different wavelengths refracting at different amounts. It is still a problem because you can't guarantee every single photon of light enters at the exact same angle. So you will have slightly different paths being taken. And the solution to this is called step index fibres. So first diagram, I showed you it's a shard of glass. It's actually not a uniform shard of glass. The core of it has got a different refractive index to the outside of it. So if we end up, I'm going to exaggerate the diagram just to make it clearer here. If we've got one ray of light enters, or if we have a second ray of light, again, always helpful to draw arrows just to be clear what's going on. They're going to catch one another. We're going to have that pulse broadening. So the centre of it, the core, has got a higher refractive index than the outside of it. Now our red line spends proportionally more time in the core than it does the outer sections, and our black line spends proportionally more time in the outer sections than it does the core. By having a lower refractive index in the outer sections, that means this black line is going to travel faster than the red line because it's spending more time in the lower refractive index. So it's a way of evening out the problem. So the red light, or the red pen here, will follow a shorter path, but it will travel slower. The black line will travel a longer path, but it will travel faster. And so that goes some way to solve that pulse broadening problem and to even out the two paths. It is still an issue, and our relay stations will still kind of reset and stop this being a problem over time. But in summary, we've got a glass fibre, Light reflects along it because of total internal reflection. We've got a cladding, an outer cladding to protect it, an inner cladding to lower refractive index and make a smaller critical angle. Material absorption is when the glass absorbs the light. We fix that by making it as pure as possible and having relay stations to boost the signal. Modal dispersion is when different wavelengths refract by different amounts to take different paths, and we fix that, and that leads to pulse broadening. We fix that with this step index fibre and relay stations, and the end result is we're able to transfer huge amounts of information through a single fibre. Lovely, thank you very much, goodbye.